So welcome everybody. My name is Stephen Feuerstein. I'm an Oracle developer advocate for PL/SQL. The Developer Advocates is a team we started up last year to both advocate for our technology into our user community, help you leverage our technology more effectively, and also act as your advocates back into the Oracle development organizations. You can see my email address. Don't hesitate to get in touch afterwards if you have any questions. Follow me on Twitter. That way you can find out news with daily tips on PL/SQL and other things relating to the PL/SQL language. And I've got a set of videos on YouTube under the Practically Perfect PL/SQL channel. And that is the title of my talk as well. Practically Perfect PL/SQL. Let's be practical about writing great code. So I've got an hour. An hour isn't very much to talk about, well, almost anything, but certainly covering a lot of stuff in PL/SQL. So I'm going to go fairly quickly. I'm going to cover things at a fairly high level. Can't get into too much detail, but hopefully I'll spur some new thoughts on your part when you write your next PL/SQL program. So before I move into the content, I do want to remind you about a great new program we just started up called the Oracle Database Developer Choice Awards, in which we'll be giving out awards to experts and community builders in 5 areas: SQL, PL/SQL, REST Data Services, Apex, and database design. And you get to pick the winners. So your votes will determine who wins the awards. Please stop by the URL you see below, or just search on Developer Choice Awards. Take a look at the different experts and place your votes. The more votes, the better for the entire community. So let's be practical. Why do I call this Practically Perfect PL/SQL? My channel, this talk. Well, we all want to do it right. We all want to write amazing, wonderful code, but somehow, something always gets in our way and messes up our plans. Too bad. So what I thought I would do is be practical about offering some tips that you all by yourself can make a big difference in how you do your programming and how you do your professional work. So in other words, you don't have to go to your manager and ask for permission to do these things or to get new tools and so on and so forth, though those things can certainly help. These will be things that you can do yourself. And all the code I reference in my talk in this PowerPoint is available online. So go to the Oracle Learning Library, the PL/SQL Learning Library, actually, oracle.com/OLL/PL/SQL, and then click on the demo zip link, and you'll have access to all the code I've got here. You can use it to reproduce the examples that I've got to do performance testing and to make sure that what I'm talking about makes sense to you in your environment on your operating system and database version. Okay, so PL/SQL tips and techniques that I want to share with you in this very short 1 hour. First, I'd like to make sure you know about the compile time warnings feature of PL/SQL and start using it. Next, at a high level, talk about best practices along the core principle is don't repeat anything. Aim for a single point of definition for everything in your application. If you can do that, you'll be writing some pretty darn amazing code in whatever language you use. Then, from the standpoint of readability and maintainability of code, I'd like to talk about keeping your executable sections really small, 10, 20, 30 lines long, to avoid spaghetti code. And then we'll cover a number of key performance optimization tips, avoiding row-by-row processing with bulk, leveraging the function result cache, and a couple of other items as well. So obviously, this is a lot to cover in an hour. And I won't get through all of it, or at least to a level that you might desire, but hopefully I'll at least get to the high points. And I've decided that with all my best practice talks, I'm going to start with compile time warnings because it's one of many things that are built into the PL/SQL language, specifically the PL/SQL compiler, that are not well used by developers but can have a really nice impact on your code. So the idea here is that the compiler mostly, and most importantly, compiles your code and makes sure that it doesn't have errors so you can run your code. But it has nothing to say about whether or not you're using the PL/SQL language optimally, only that your code is syntactically correct and you're referencing objects that you have privileges to access. PL/SQL also offers a compile time warnings feature that answers or addresses the side of optimal code. It offers advice about ways to improve the quality of your code and perhaps even the performance of your code, and does so automatically, but you've got to turn it on. So what you can do is go to the Oracle Database Error Messages document and check out the different warnings they have. In fact, let's just go right there for starters. I should have had the page all ready to go, but sorry I didn't. So let's go to the Oracle doc. Oracle doc. Now known as the Oracle Help Center. We'll drill down into database. Bring up all the books. Go to Error Messages Manual. So here you see the list of all the different Oracle errors, the different categories. And if you go to PLS, you'll find the PL SQL compile time errors. These are all the errors that the compiler might raise about your code. And of course, there are a lot of them. But right below PLS is PLW. And PLW are the warnings. So these are the different things that the compiler will give you feedback on to help you improve the quality of your code. Not as many as there are errors, and the list was surely to grow over time. So that's where you can go to see what all the warnings are. Let's take a look at how you can actually leverage this functionality in your day-to-day work as developers. So first of all, by default, compile time warnings are turned off, and you can enable them with an alter session statement, set PL SQL warnings, and you can simply enable them all. Or you can enable a subset, for example, all the performance category, enable an individual warning. You can even set an individual warning to be a hard compilation error. Let's take a look at some code. So here's SQL Developer, and first of all, note that if I go into Preferences and type Warnings, it'll take me to the PL SQL compiler page. And right here, I can enable all warnings. I can enable just an individual category and so on. So you've got a UI that will automatically set your warning status when you log in, when you connect. So I've got enable all. Great. So let's take a look at some code. So this is the zip file, the demo zip that I told you about, all the code that you have access to. And a number of files start with PLW. And these are all different examples of the warnings analysis.
Now, first of all, I'm going to get rid of this first statement. I'll come back to that in a moment. Here's a piece of code that is completely valid. Oracle will compile this, and you will be able to run it. If I compile it, yes, we get warnings. I'll come back to that, but there are no PL SQL errors. I can execute this code. In fact, let's execute this code. Begin PLW. End. Execute. Oh no, numeric or value error, character string buffer too small. So I run this program and I get an error, and you know what? I bet you knew that. I bet you knew you were going to see that error because it's pretty darn obvious, isn't it? I'm assigning ABC to a string with a maximum length of 1. And you might have been saying to yourself for so many years, Oracle, why can't you figure that out too? You're so smart. Well, in fact, Oracle is super, super smart. The software. And you can do that by turning on PL SQL warnings. So here's a statement that says, let's enable all PL SQL warnings. I execute that. And then I compile my program once again. Now let's take a look at these warnings at the bottom. I get 3 warnings. One is that an operation will raise an exception. Second, unreachable code. Third, an operation will raise an exception. We're going to focus on the 6017 in this example, and I'll show you in more detail unreachable code, but I will explain why it's showing up here in just a moment. So what you're seeing is that the Oracle compiler is in fact super smart, and it's detected that this string is too big for this declaration. This is going to cause an error. It also noticed, hey, you're doing a divide by 0. You're not supposed to do that. So what it's doing at compile time is saying, you know what, this code is correct. You can run it if you want to, but we guarantee you're going to get an exception. Notice it doesn't tell you where you're going to get the exception, just that you will. Now that, in a nutshell, is the power of compile time warnings. You ask the PL SQL compiler to give you feedback on the quality of your code, and it applies a whole bunch of different rules, and we'll take a look at those rules in the error messages manual in just a moment, to give you advice about how to improve quality of code. In this case, the quality is a pretty significant one. You're going to get an error. In some cases, it's a little bit more interesting or subtle. So for example, the second warning listed in this strip here, unreachable code. So why do we see a message about unreachable code? Well, what it's noticed here is that if the exception is raised in this statement, you're never going to get here. So this line will never be executed. Oh, and by the way, it's also going to raise an exception. So that's a hint that Oracle also does unreachability analysis. Let's take a look at that. And I'm going to tell you how to get a hold of all my scripts and use them at the end of my presentation. So I've enabled warnings, and I'm going to, again, compile. And I get two warnings, unreachable code and uncalled procedure. First of all, unreachable code. So what it's noticed here, and again, you can probably sort it out yourself because it's a simple program, L checking is declared to be false. So this is never true. This line of code never executes. And by the way, in another variation of unreachability, it's also noticed that I've defined a nested subprogram, but that program is never actually executed. So it just tells me I removed it. It actually removed the code as it went through the compilation. That's part of the optimization process. So again, for a simple program like this, you could eyeball it yourself and say, well, that's ridiculous. This code's never going to get executed. But in more complex scenarios, that's not going to be very easy to do. And so instead, you might never notice that entire blocks of code never can possibly theoretically be executed. So you just flip that switch, run it across your big packages, and you never know what sort of amazing surprises you are going to find. Let's take a look at one more example of the kind of warnings that you can get. Then I'm going to show you how to set it up in PL SQL Developer. We'll take a look at the error messages manual and sum up. So PLW 5005, this is one of my favorite warnings in terms of why it should be an error instead of a warning. So I'll show you how you can do that too. So I'm going to define a function, a couple of functions. These are being called by my main function. And here's my main function, no return, hint there. And when I compile this function, actually, let's run it first. So I will compile it. We'll ignore the warnings right now, but let's run it. I try to run no return, and my script output shows me, oh no, function return without value. Now this is a runtime error that I would hope you never see, and I'm always embarrassed when I get it. What this is saying to a user who runs your code is, oh my gosh, Stephen never even tried this code. If he tried it, he would have noticed it doesn't even return a value. So it's a very embarrassing kind of error to get. And of course, we can now flag it with the PL SQL compile time warning. So now when I compile, take a look. Subprogram no return returns without value. It doesn't tell me what line of code is the problem. Now we can look at this code and say, here's the problem. There's no return here. But it doesn't try to do that kind of analysis. It simply says by the time you get here, there's a chance that through one branch of logic, one flow, you might not have executed a return at all. The classic solution here, by the way, is to have a single return statement as the last line of your function body. And then instead of returning all over the place, you simply assign values and so on and so forth. But again, it's flagging a compile time, a real serious problem with the design of your code. You can then go in and fix it and make sure that you never get the function returns with that value runtime error. So a whole bunch of warnings are really critical stuff. Some of them are perhaps a little bit more along the lines of a nuisance for you. For example, I often get this one, 5018, no return omitted optional auth ID clause. So as many of you probably don't know, there's an auth ID clause for procedures, functions, and packages which sets it up as definer rights or invoker rights. It's a feature of invoker rights is a feature that not many developers use, so they don't add the auth ID clause. It's good to put it here because it's a way of defining explicitly that this is running under definer rights, but also it's a reminder to other people who come along that there's a feature that this clause relates to, and they might go look it up and learn about something they can do with PL SQL, which is another really nice aspect all around to compile time warnings. I'll give you another example of that. I'm going to make this parameter in out. Compile. Now I get a silly error because I've introduced some code that forces a real compile error. And let's see. Okay, now you see we have another warning, 7203. Parameter check-in may benefit from the use of the NOCOPY compiler hint. Because I've set it up to be an in-out parameter, Oracle's going to do a copy in and copy out, which can give you some overhead and performance drag. And if you add the NOCOPY hint, you will avoid that copy in and copy out and possibly make your code run faster. My point here is that, again, the compile time warnings are an opportunity for you to learn more about PL SQL. You might never have heard of NOCOPY, but if you use warnings, now you have learned about it, or you at least have a heads up about it. You can go explore further. One more thing for the 5005. If you said to yourselves, boy, I hate getting that function does not return value error. I want to make sure that my function can't compile when it has that warning. I can say error 5005. Alter my session. Compile my code. And now take a look. Now it says PLS 5005, subprogram no return returns with that value. Instead of PLW, it is no longer a warning. It is now a hard compile error. I cannot use this program unless this warning is addressed. Unless I make sure that there's a return on every branch, which I could do really dumbly here. I could say return null, which is probably not the thing to do. Now I no longer have the error or warning. So if you find some warnings that you think are super critical that you never want to see manifested in your production code, set them up to be errors.
So my suggestion is to always turn on warnings. Enable all of them. In fact, you can get really severe and enable all warnings as errors so that your code will never be usable, will not compile, unless you've actually gotten rid of all warnings and you have a clean compilation. So that's my quick delving, unsuccessfully actually, into compile time warnings. My apologies for not getting that sorted out before I started my talk. But if you rely on the compile time warnings, it'll give you information about your code. It'll give you information about features of PL SQL you may not have been aware of. Okay, so let's move into some core best practice tips and performance tips for PL SQL. First of all, just generally, don't repeat anything. Whenever you repeat stuff in your code, literal values, formulas, etc., you're essentially committing an act of hard coding. You have it in more than one place with the underlying belief, the assumed belief, that you're never going to need to change it. And of course you do. So you're setting yourself up for failure. And one of the things I like to point out about hard coding and avoiding repetition is that you need to expand your definition of what hard coding is. Because for the most part, we think of it as being literal values. So for example, I think that you should consider every constrained declaration like a varchar 100 to be a hard coding, in fact, to be a bug. I suggest also that every single SQL statement you ever write is a hard coding, and the worst kind of all. And then, of course, business rules and formulas. So you do need to write these things. And in fact, PL SQL is a really good place to write them, your business logic, your SQL statements. And the trick, therefore, is to figure out how to define a single point of definition to avoid repetition. So I'm going to explore a couple of examples of those, again, quite likely. First of all, I suggest that you consider every varchar2 declaration in your code to be a bug unless it's the actual single point of definition. So for example, in this tiny little piece of code, I've actually got 3 bugs. I'll go back over that in a moment. But notice my full name, varchar 100. Now, I don't know if you've ever had this feeling. You're typing code, you declare a variable's name, you type varchar2, and as you get to that number, open paren, your fingers kind of freeze up. What do I put there? 10? 100? 32,767? It can never get bigger than that. And what you see here is a classic example of hard coding that reflects your current perception of the world. So the full name is concatenation of first and last. This one's max 20. This one's max 25. That's 45 plus 1 is 46. I'm going to make it twice that, 100. It's never going to get to be that big. Oh, and I need to declare a variable that's the biggest string possible. So I'll declare it as 32,767. It's never going to get bigger than that. Now, my suggestion is that whenever you're talking to a developer or you're listening to yourself talk and you hear the word never or the word always, you should ask yourself, am I putting a bug in my code right now? Because as soon as you're saying that, you're most likely falling into the trap of thinking that things aren't going to change, and they do change. And by the way, the third bug in this piece of code is the hard coding of my formula, first space last, as the full name. Anyway, here's my suggestion. When you're looking at constrained declarations, varchar2n, number 9, 2, etc., you should always find a way to hide that declaration behind a name, preferably with %type and %row type anchored declarations, or create subtypes, which is the main feature I wanted to make sure you were aware of. Let's take a look. The hard coding script has lots of different examples of hard coding. The main thing I wanted to look at right now was this one. So what do? I've got last comma first. I need to fetch it into a variable. I need to declare it somehow, but I can't declare it with %type because it's a concatenated value, a derived value. So what you should consider doing instead, oops, is declare a subtype. So you can create your own named application-specific types. My full name, T, is varchar2200. I declare it once here. And then whenever I'm writing my code, rather than fumbling over what the maximum length should be, I can write employees rules package, full name, T, and I'm done. So I describe by name what this thing holds. And then if it ever needs to change, if 200 is too small, okay, I'll change it to 2000 right here in one place, recompile, and all my references are automatically with a compilation. Reset. So that's what I mean about a single point of definition for something as simple as constrained declarations. Let's keep going. On a much more fundamental level, let's talk about hard coding select statements, SQL statements in general. So my suggestion to you is that every SQL statement you ever write is a hard coding and should be avoided. And the main thing, of course, is to avoid repeating the same statement. Now, this slide is all about a very strange dynamic in organizations. When I give presentations, it's not uncommon for people to have PL SQL coding standards. Hopefully you have something yourself, how to name variables, some guidelines about writing your code. But very few of those same organizations have any guidelines that give any direction about when, where, and how to write SQL statements, which is very strange because SQL statements are one of the most important aspects of your application, most likely to cause tuning problems, and data integrity issues, all sorts of problems. And yet we don't have any controls around when and where and how to write them. We just do whatever we want, whenever we want to. And the net result is an application that has SQL statements dispersed throughout the entire application. Anywhere and everywhere you need to get data, you write a select statement. Anywhere and everywhere you need to make a change, you execute a DML statement, insert, update, delete, directly in your application code. And that, I think, is a really bad idea. It makes your application difficult to enhance, optimize, and debug. So in terms of SQL statements as hard coding, I'm not going to go through all my spiel around why it is, but just think about it this way. Every time you write a SQL statement, all you're really saying is that at this moment, this SQL statement meets the given requirements that I've got. Will those requirements ever change? You know they will. So you will have to go back to the SQL statement and change it. And if that same or similar SQL statement is in multiple places in your code, how do you find those repetitions? How do you manage that? So the bottom line suggestion that I encourage you strongly to consider is create a data API, a data access layer, essentially one or more packages on top of tables or transaction units, business objects, that have subprograms that do the work for you. So if I need to do an insert, I call the insert procedure. If I need to get a row of data, I execute a function that returns that information. And it's all hidden inside a PL SQL API, which means you're much less likely to have multiple versions of the same SQL statement. And it's much easier to optimize because you've got one place to go to. Essentially, you want to think of SQL as a service that's provided to you, not something you write over and over and over again. So again, the basic idea is that in between your tables and your application level code, whether it's in JavaScript or Java or Python or even PL SQL, any code that's written specifically for user requirements, you put a layer of code in between, usually one or more packages. And that layer of code kind of intercepts requests from the application code, make sure that integrity is followed, make sure that they only can see the data they're allowed to see, and make sure that the operations against the baseline tables occur properly. There are so many benefits to this approach. The key thing is putting the rules in place that allow you to do it and either generate these kinds of packages or build them by hand. But the main thing to keep in mind is you want to write any specific SQL statement just once and then leverage that throughout your entire code base. So moving on through the idea of single point of definition, avoid hard coding, hard coding of business rules and formulas. I would think this should be pretty obvious, right? You don't want to expose the rules and formulas because they change and get complicated over time. Now, generally speaking, what you want to do is take those rules and formulas and move them into functions. And one of the challenges can be realizing where you have rules showing up in your code. So before I show you this code, let's go back to SQL Developer for a moment, to my hard coding script, which you can download and check out on your own time as well. There are actually at least two different formulas that are shown on this page. And you might want to take a look around and see if you can find them. Here's one, last comma first. So the documentation says the full name of a person is last comma first. Well, that's easy to write. I'll write it here, I'll write it there, I'll write it everywhere. Here's another rule. If the salary is greater than 10 million, that defines who the CEO is. Well, that's likely to change, right? Your CEO might say, I don't deserve $10 million or $11 million. I deserve $1 million, and I should give all the rest to the developers in my organization. So the rule could change, but the point is that these kind of very simple rules are the ones that often escape our attention and don't motivate us to hide them, to encapsulate them behind functions. So let me show you another example of that now. This is a useful thing to know about PL SQL generally. So inside the DB Mesh Utility package, there's a program called getTime and also getCPUTime. And you can use these programs to calculate elapsed time down to the 100th of a second. So for example, I call getTime to get the start time. I run my code, and then I get the delta between the current getTime and the original starting getTime. And that shows me the number of hundreds of seconds that have elapsed. That's a very simple formula. And you could write scripts like this, utilizing this functionality, to build a number of test scripts. I suggest you do not do that. You're exposing the rule, n minus start. Oh, but it's so simple. It's never going to change. Yeah, but maybe it's not even correct. So here's what I do. I build these packages like my timer package, and I say start the timer, run my code, show the elapsed time. In other words, I hide it behind an API, a programmatic interface. Now, why would I do that? Well, oddly enough, it turns out that for something as simple as n minus start to get my delta of time could not be true. Under some circumstances, it might give me a very large negative value. Here's the problem. With getTime or getCPUTime, it starts off at a 0 point, and then the clock ticks and the hundreds of seconds accumulate. And then it reaches an operating system limit, and then it rolls around a 0 and starts counting again. So if I call getCPUTime to get my start time just before the rollover, and then call my end time a second or two later, I can end up with a massively negative elapsed time. So the real formula for calculating elapsed time is take end minus start, add a really big number to it, and then mod by that number. Now, if I told you that this is the formula, I bet there's a really good chance that you would never, ever write that formula here in your different scripts because it's too weird and it's too hard to remember and so on and so forth. But when there's simple rules, you say to yourself, not only is that easy to write, but it's never going to change. So if you're try to build up some sensitivity as you're writing your code to exposing these rules and formulas, and stop what you're doing, take a moment or two to build that API. They can often be very simple, very focused packages. And then you go to that one place where the rule is defined and change it there, and nobody has to go and update all their different scripts. I think you're probably getting the idea. So moving on from avoiding repetition, I want to talk about the piece of advice that is probably could have the single most largest impact on your code quality. And that is keep your executable sections tiny. So you've probably all heard of spaghetti code, right? I've written spaghetti code. I'm sure you have too. The worst thing about spaghetti code is when you have to maintain your own spaghetti code, which I still do on occasion. It's nice when you can write awful code and then hand it off to somebody when you leave for the next job. It's not nice. It's a very bad thing to do, but there it is. So spaghetti code is when you're writing code and writing code and writing code, and you're on line 754, and you're typing end loop, and you don't even remember what loop it is you're ending. You have these long, twisted up, convoluted executable sections that go on forever that you don't understand, and you wrote it, and nobody else can make heads or tail of it as well. So fortunately, it's actually quite easy to make spaghetti code a thing of the past. Never write it again. All you have to do is follow this one piece of advice. Organize your code so that any executable section of a block has no more than 50 or 60 lines of code. The basic idea for the original piece of advice in this size is these are the number of lines that would fit on a single piece of paper or a single screen. And therefore, at a glance, you could see the entire logical flow at this level of detail. Now, obviously, your programs have a lot more than 50 lines of code in them. I'm not saying that you can write applications in 50 lines of code. I'm talking about how to organize that code. Let's take a look at an example. InTab DBMS. So I wrote a program called InTab, which essentially is select star from table in PL SQL. And in the original version, let's see, original bad version, it uses dynamic SQL method for you pass the name of the table, it looks up the columns, it constructs the SQL statement, executes it, gets the data. It was pretty long, 335 lines long, and here's the executable section. Starting here. I've got some comments. Wow, that's exciting. Now, I could just take you through this code and explain everything I'm doing, and I have to explain it, whether in comments or personally going through it with you. It's a lot of code. Yuck. Here's the same approach, and clearly this violates my rule of 50 lines in the executable section. You know what? I'm going to make my font size a little bit smaller. We don't need all this. So, lots and lots of code. Here's the approach I took using the technique that I'm going to introduce to you to make your code vastly more readable, and that is called the nested subprogram. So, inside any declaration section of a block, you can declare types. There's a subtype hiding the maximum size var_2. I can declare variables, I can declare types, all sorts of stuff. And I can also declare other programs, functions, and procedures. These are called nested subprograms. They can only be accessed inside and by the code in this parent procedure. Now, let's go down to the very bottom of this program. Check it out. My entire executable section for this procedure is 5 lines long. It's the table of contents. I can read it to you. You can read it yourself. Load column information, then construct and parse the query, define the columns and execute, build and display the output. So what I've done is taken my original bad implementation with the code that goes on and on and on, and I've said, oh, what does this code do? Let's take that code. Oh, I know what that does. That gets the column information. I can right-click, refactor, extract procedure, and I could say get column info. Sometimes it works. Sometimes it doesn't. This was working just the other day. I don't know why. Anyway, what you can do, since it's not doing it by itself, is grab that code, right? Get column info. Come up to my declaration section, procedure. Get column info is begin. And I've now created a nested subprogram. And I've replaced a bunch of code that was sitting in my declaration section. And notice now, as I go through my existing code, so in other words, you can refactor existing spaghetti code or use this as an introductory step when you're building new code, I can chunk down all this code into a sequence of named elements that makes my code inherently so much more readable. And even within any of these subprograms, I can create other subprograms. Here's a good example. Build and display output has within it display header. It's got some complex string manipulation stuff in it. So rather than junk up my main section with all that code, I just hide it away and say display the header. If you need to see the details of display header, you drill down to that. Otherwise, it's out of your way. So this one tip, use nested subprograms to modularize your complex executable sections, will dramatically transform the quality of your code. This one step could make your code much easier to maintain, much easier to understand. And I strongly encourage you to start doing this. Over time, you'll find that you'll get allergic to long blocks of code. You'll start writing code and you'll get to 30, 40, 50, 60 lines and you'll start to get nervous. Sweat breaks out on your brow. This is too long. I should chunk it down. And you'll just condition yourself to write extremely readable, highly manageable code. Oops. So again, check out your extract procedure refactoring. I know it's in Toad and SQL Developer as well. I'm not sure why it wasn't working for me just at that moment, but it can definitely help automate the process. Alrighty, so 9:35. I left half the time for optimization tips. Not bad, but I'm going to have to optimize the way I present my optimization tips. So We're going to take a look at avoiding row-by-row processing with bulk processing, especially FORALL. Take a look at the function result cache added in 11G. Go over the NOCOPY hint, a nice, simple, quick way to improve performance of some kinds of code. And I'll talk to you about a new feature in 12C that improves the execution of calling functions in SQL. Diving right in. So avoid row-by-row processing. If any of you follow Tom Kite, the mantra has been row-by-row is slow by slow. And it can be quite perplexing for developers, partly because we have come to believe that PL/SQL and SQL are so tightly integrated. And in some ways, it is. Here's a very elegant piece of code that showcases the power of PL/SQL. I can declare a cursor with native SQL in it. I don't have to write JDBC or ODBC code or whatever. I've got this elegant cursor for loop that takes care of the opening, the fetching, the closing. I can execute my code within the loop, and I can even execute native DML statements. Really nice, short, concise code. And this is the kind of code that you should never see in production, at least if you're working with a reasonable amount of data, because this involves row-by-row processing. Get a row, update a row, get a row, update a row, over and over and over again. Now, I'm going to go into some more detail on this, but the bottom line is that you should never see non-query DML, inserts, updates, deletes, inside a loop. If you ever see this, you should do one of two things. First, you should ask yourself, can I replace it with a single SQL statement? Do I need PL/SQL here? For example, depending on what adjust compensation does, we might be able to get rid of this whole thing, this whole PL/SQL block, and replace it with a single update statement. If this is doing some complex computations that have to occur outside of a SQL statement, then you need to look at using bulk processing. Now, why do we have a problem with performance here? Well, take a look at this little movie. But the bottom line, as this is going, is that even though PL/SQL and SQL are syntactically tightly integrated, the reality under the covers is that there's a separate engine to run PL/SQL statements and another engine to run SQL statements. And whenever the PL/SQL engine hits a SQL statement, it says, wait a minute, stop, prepare that statement, send it over to the SQL engine, it does its thing, sends the information back. And each one of those switches, it's called a context switch, is overhead of performance. And it can be quite a bottleneck in the performance of your application. So what you want to do in general is reduce the number of context switches. And bulk processing gives you a way to do that. So if I have a for loop, and inside it I have one or multiple DML statements, and I can't switch to just straight SQL, I need PL/SQL, then what I can do, what you should do, is switch from a for loop to a FORALL statement. It's like a meta DML statement. You attach the DML statement to it, and then the behavior is very different. When the PL/SQL engine hits that statement, it says, oh, I know what you want. You want to batch up a whole lot of update statements, and I'll send them across to the SQL engine for you in one switch. The SQL engine will do all the same stuff it used to do. In other words, if it executed 1,000 updates, it'll still execute 1,000 updates, but without going back and forth. And that one change can lead to dramatic improvements in performance, easily for DML, an order of magnitude and improvement of performance, which is pretty substantial to achieve just in PL/SQL code. Now, I don't have a lot of time to go into all the details of this approach. The bottom line is that you should always look for opportunities to switch to bulk, move away from row-by-row processing. Changing, however, from that integrated row-by-row approach to a phased approach, which is what you get to with bulk processing, is very much non-trivial, and it can involve a lot of change to your code. Basically, in general, you're going to get data out of your table using bulk collect. And I'll show you some examples in just a moment. You're going to populate collections, arrays. Then you're going to act on those arrays in PL/SQL. You might need to delete some rows, change values in rows. And then you're going to push data back to the same or different tables using FORALL. Again, the time in this talk to cover this is quite limited, but let's just give you a brief look. Here's an example of my non-bulk approach. For every record in my employee, for every employee in this department, insert a row into the history table with their current salary, adjust their compensation with some sort of crazy formula, and then update the employee with that new salary. If anything goes wrong, log the error and keep on going. Now, this program shows actually the power of PL/SQL constructs, the fact that I can have a begin inside my loop. I can constrain the exception propagation, log it and keep going. If the insert fails, never do the update. There are all sorts of things built into PL/SQL that are very appealing and very concise. but this could be too slow. So I'm going to switch over to the bulk approach. Notice, first of all, that my program, which is, let's see, 22 to 52, 30 lines long, is now 117 lines long. It's a lot longer. It's a lot more complicated. It's a trade-off you'll have to make. And here's my nicely modularized with nested subprograms executable section. Fetch the next n number of rows, like 100 at a time or 1,000 at a time with bulk collect. That's the query side of bulk processing. Then insert the history rows, adjust the compensation, update the employees. So now we do it in phases. Insert 100 history, update 100 employees. And here's what I've done. Rather than doing a single insert, I use FORALL for all the elements in this collection. Construct the insert statement, pass and bind variables from the different arrays, and then execute them. If anything went wrong, I have save exceptions turned on. If anything went wrong, save the exception information, and then iterate through the arrays of errors and log those errors. And then remove those employee IDs from my list of employees, so when I get to the update section, I will not be updating any rows for which an insert failed. Then I have a FORALL statement with save exceptions again to save exceptions, and a new format for my FORALL statement called indices of, which allows me to work with sparse arrays. Obviously, this feature is deep and has many different aspects to it. Can't cover them all today, but the main thing to remember, jumping right back to good old PowerPoint, is that whenever possible, use bulk processing. Well, whenever possible, do it all in SQL. Whenever you've got DML inside a loop, if you can't do it in SQL, switch to bulk processing, and you will be a hero on your team. Now, hopefully, you've already used this feature throughout your entire application code base, and there are no more opportunities to use FORALL because it's been around since Oracle 8i. But do go back and check. And if you're using Toad, you can use the code analysis feature, and it will actually identify places in your code where it's finding DML statements inside your loops and automatically tell you how to fix it, or at least recommend that you fix it. Okay, zooming right along. The function result cache. This was introduced in Oracle Database 11g, and you can use it to improve performance of a number of different scenarios, but certainly of repeated queries against unchanged data. So let's say I have a materialized view. It's not changing during user, well, it never changes, except for when it's being refreshed. And yet we hammer that materialized view. We query the results over and over and over again, the same rows, the same queries again and again. And we pay a price to go through the SQL engine to get to it. But if I put that query inside a function and result cache it, then I can avoid going back and getting that data again and again because it's already been fetched and it hasn't changed. And so it can give you some significant improvements in query performance. You can also have a complex application configuration value that you want to execute just once and then cache it so you don't have to repeatedly execute it across your database instance. So I'm going to explore this rather quickly, but do keep in mind possible read consistency issues when you're using the function result cache. In general, let's see if I've got a quick script I can drive this point home around on. Sometimes I don't remember the names of my own files. Cursors and context switches. Here's the point I want to make about read consistency. If I have a function, let's say my EM meme summary, and I select data from it, one of the nice things about functions in PL SQL is that you can call them in SQL. So here we go. Here's a select statement inside a procedure, and it calls a function, and that function in return calls a select statement. And I'm going to show you that you can result cache. I can put result cache on this function. So that's how it applies to the section. Here's the thing to keep in mind. As you probably know, you should know, Oracle keeps read consistency available for us in our applications. So for example, when I have this cursor going, I select title from this table. For the duration of the execution of this cursor for loop, any changes to this table are not reflected in the select statement. So if I've selected row 1, and before I get to row 2, somebody has deleted that row, I will not see that deletion. I'll still see the data because Oracle's keeping a read consistent image of the database from the time I started my SQL statement. However, in general, if you call a PL SQL function inside your select statement and it has SQL inside of it, this SQL statement is not included in the read consistent image that's managed by the outer select statement. So in general, whenever you're calling functions inside SQL, and those functions have SQL in turn inside them, you need to be very careful about potential read consistency issues. Now, the result cache is stored in the SGA, it's shared across sessions, and it's automatically purged of dirty data. The function result cache is a really amazing and elegant feature, available in Enterprise Edition only. But again, you do need to be careful about using it right. Now, how does it work? Well, essentially, you have to make one change to your function. You add a single keyword, result cache, to the clause of your function's header. And then every time anybody in the database instance makes a call to that function, Oracle takes a look at all the in-argument values. It can only have in-arguments. And it asks, has somebody already called this function with the same in-argument values? If it doesn't find a match, then the function is executed, and the inputs and the return data are cached. If Oracle does find a match in the cache, in other words, there's essentially a unique index on the in-argument values, if a match is found, then the function is not executed. The values are simply returned. So we avoid function execution, we avoid SQL statement execution. And Oracle automatically, as of 11.2, tracks the tables on which your function is relied. And if anybody makes a change to that table and commits them, then the cache is automatically marked invalid and will have to be rebuilt. So Oracle will automatically make sure that nobody gets dirty data out of the cache. Pretty cool stuff. Let's take a look. Let's close down these files. So here I've got a demo package, and I've got a function last name, passing the employee ID, return the last name, and I've added the result cache keyword. That's all I have to do in there in the package body. Inside the body, notice I'm displaying a message when my function is executed, then I get and return the last name. Great. Let's compile all that. Let's see. Let's just refresh this. Run my script. Compiles everything. And let's then now execute it. So what I'm going to do is execute the same function call 10 times, passing in the same value. Let's turn on DBMS output. And let's see what happens. I'll run my script. I look at the output. Notice, executed the body of function just once, returns the value, and then for all the other times, the function is not executed. And watch this. I'm going to disconnect. I'm going to reconnect. So it's a fresh session. I'm going to run the same code. And I forgot to turn on output. Darn it. So I'm going to run the same code. And notice, the function is not executed still. Even with a fresh connection, a fresh session, the function body is not executed because this cache is across the entire instance. Whether I'm connected to Scott, HR, or whatever, it'll all reference that same cache. Very cool stuff. So again, the only thing you have to do is add the result cache keyword. If you're on 11.1, you had to add relies on. We had to actually tell Oracle which tables our function relied on. That's no longer necessary in 11.2 and higher. That clause is entirely ignored. Let's take a look at the performance impact. So I'm going to create 3 different packages, all getting data, all getting rows of data from the employees table. So the first approach is the traditional approach. I've encapsulated my select statement inside a function, passing the ID, return the record. Every time I call this function, the select statement is executed. In the second approach, I'm going to use what's called the PGA caching. I'm going to create a variable at the package level, my package body, that has the same structure as the employees table. And as soon as this package is utilized, the initialization section will run, and I will take all the data from the table and move it into my associative array, my cache, using the primary key as the index value. I don't have time to go into all the explanations of this one. If you're not familiar with Oracle PL/SQL collections, you definitely need to explore them in more detail, and perhaps we can do a separate session on that. But essentially, I've copied the entire table into memory, and I'm now my function one row simply goes to that location in my cache and returns it. Very fast caching, but it's got a lot of drawbacks I'll come back to. And then finally, my result cache function. I've gone back to my original package, and I've simply added result cache. And I've got some fancy code here that says if I'm on 11.1, include relies on. This is called conditional compilation. So let's take all of this code and compile it. There's my compiler. There's my compiler window. Maybe I should go back and show you the compile time warnings now. Okay, so now let's take a look at the performance. Let's pull you down here somewhere. Okay. So let's take a look at comparing the performance of these things. Here's a procedure, test employee lookup, that allows me to basically execute the same code multiple times for my different approaches. Use my timer package to compare the performance. I compile this. Notice I've got a warning. Here we go. Sorry it came late in the game, but there's my warning. I forgot my auth ID clause. You might not even know what the auth ID clause is, and that's what I meant about it teaching you about new things in PL/SQL. Now I want to clean compile. There we go, clean compile. Okay, so I've created that program. Now I want to test it. So let's run this procedure. I'm going to execute it 100,000 times, and I'll pass in 138, which is a valid value. I execute my code. Make sure my dbms output is turned on. So what it's doing now is essentially 300,000 queries or lookups, and check out the performance. When I execute the query every time, it took over 2 seconds, which is not bad for 100,000 queries. Caching the table in PGA memory, 0.04 seconds. That's amazing. Look at the difference. Because all I'm doing is going in my own personal PGA cache from my session, not to shared memory. Super fast, but it's a feature, or it's a technique that is very limited in usefulness because you can't share the cache with others. It has to be a completely static table. You're responsible for maintaining the integrity of your cache. But check out the Oracle 11g function result cache. 0.09 seconds instead of 2 seconds. Incredible improvements at 2 orders of magnitude improvement in performance. And this is a cache that Oracle is automatically managing, automatically keeping valid. You don't have to do any of the work except putting the result cache keyword onto your function definition. Wow. That, in a nutshell, is the function result cache. And it is an awesome feature. But as with any other feature of Oracle database, you got to use it with care. Whenever you're doing caching, you have the danger of stale data. And there are a number of complications in using the function result cache, which I can't get into today. But it's easy to abuse things like the result cache. So mainly the thing to remember is you got to watch out for session-specific dependencies in your function. One of the biggest, most prominent ones of those is going to be virtual private database. I don't know if you use that at Anthem or your company, in case other people watch this video, but virtual private database is a powerful feature that offers row-level security, and it can really mess with the function result cache. Watch out for potential read consistency errors, and work with your DBA to make sure the result cache pool size is set properly and avoid possible latching issues. Cruising through the last couple of topics, NOCOPY parameter hint. Let's just take a look at some code. Here's the thing to keep in mind. If you ever have an in-out parameter or an out parameter, then Oracle passes these values by value, not by reference. And that means that inside your program, as you make changes to that data structure, you're not changing the actual thing that was passed in. You're changing a local copy. And if the program terminates without an exception, then that local copy is copied back onto your actual. So here's the actual thing I'm passing in to my procedure. But when it's an in-out parameter, I'm not going to actually change this thing until I'm done with my procedure and it's finished without any kind of errors. So you copy in and you copy out using memory and CPU. But if you add the no copy hint to your outer and out declarations, then what you're saying is I'm passing by reference, and any changes will be made directly to the thing I passed in, not to a copy. I'll avoid the copy in and copy out. And you can see a nice improvement in performance if you've got large arrays or large objects and record structures. So consider using no copy for any of your out and in-out parameters. Your warnings subsystem will tell you about that. Final tip, optimizing function execution in SQL. So this is a 12c new feature. You're probably not on 12 yet, but hopefully you will be soon. And there are basically two things that Oracle has done in 12c to help with this aspect of utilizing, calling your own functions inside PL SQL. The first is a with clause in which you can define PL SQL functions inside SQL. And the second, and more importantly, from a standpoint of performance, is the UDF PRAGMA. Let's just take a look at the code. Again, in my demo zip, if you look for any file starting with 12c, you'll see demonstrations of all the different features, new features in PL SQL for PL SQL developers. So let's take a look at the with clause first. Where are you? With function. Now, hopefully you're familiar with the with clause from the past, which is called subquery factoring. You can actually create, let's show you this. Sorry. So prior to 12c, you could already do things like this. You can have a with clause in your SQL statement, and I can define sub-selects, give them names, and then reference them by name in my subsequent with clauses and the main bodies of your statements. Basically, what you can do with the with clause is modularize your SQL statements. So if you're not already doing that, please check it out. In 12c, it was extended to allow you to implement PL SQL functions inside SQL. Now, why would you do this? Well, essentially, if you have some relatively simple computations that you're executing in multiple places in your SQL statement, you can now modularize them into PL SQL with a minimized overhead of calling that PL SQL function, reduced context switch cost. In addition, if you're running in a read-only database, like an archive database in which you can't create PL SQL functions at all, but you can only execute select statements, now you can put functions, your PL SQL functions, inside the select statement and get some additional functionality out of those queries. Performance-wise, it helps a little bit, not as much as the UDF PRAGMA, primarily because of an existing bug. So let's take a look at the UDF PRAGMA, which is more interesting from the standpoint of performance. So in 12.1 and higher, you can add a PRAGMA UDF. It's a compiler directive, a command to the compiler. And what you're saying when you add this PRAGMA is, hey, PL SQL compiler, I am almost always going to call this function from within SQL. It's a user-defined function. They all are, really, but anyway, a UDF from the context of SQL. I'm going to always run it in SQL. So why don't you prepare it for me? So basically what happens when you include the PRAGMA is that the PL SQL compiler does at compile time more of what it used to do or would do at runtime. So when I call my function inside a select statement, basically the PL SQL engine and then the SQL engine have to prepare the data set, the data for some conversion between types and things like that. But if I declare it as a UDF PRAGMA, then it does some of that work upfront at compile time, and at runtime, the cost of doing the context switch is reduced. So when you're building functions that you know almost always will be executed in SQL, add the PRAGMA, and you get some quick and easy performance boosts. All right, wrapping up. Practically perfect PL SQL, it's all up to you. You can do it. In a very practical way, you can write much more perfect and maintainable and high-performance code. First of all, you can turn on compile time warnings. You can aim for a 100% clean compile. You can make sure that you're getting all the feedback possible from the PL SQL development team about how to make maximum use of the PL SQL language. You can become more sensitive to hard codings and hide them behind a single point of definition, most importantly with your SQL statements, and use those nested subprograms to make highly modular, readable code, which of course is actually the next point. Control the size of executable sections so you can write very readable code. You can definitely greatly improve performance of your PL SQL programs whenever you can find any DML statements inside loops. Look for opportunities to apply the function result cache. Work with your DBAs to make sure you've got things set up properly to leverage it. Look for opportunities to apply NOCOPY and the UDF function. And just these alone, and there are many more tips we can go into, and a lot more detail, of course, but just by following these recommendations and these features, you can have a significant impact on the quality, maintainability of your PL SQL code.